It's not particularly exciting. Same as the other one.
I'd be more excited if I was waiting for a big one.
Yeah.
Yeah, that's true.
Turn it on, it spins, electrons flow.
Are we gonna
It's a
be
better switch
using
though,
like
right?
this?
So the red dots are the protons?
The red dots are the electrons moving from the negative potential up to the positive potential. Electrons always go negative to positive.
Are we gonna be using this program at any point? Or are we
No.
just doing Snap?
Yeah, we're going to. And the other thing here, we have two. There are two multimeters that we're measuring the charge, the current. They both said the same number, 0.6 amps, because in series the current shall be the same. It's getting freaky on me now.
Wait, I thought you had said that the red dots were photons.
If I said that, I misspoke.
The electrons.
The electrons are moving from negative to positive.
Why do you even say mutant?
Bangarang.
Red tights.
Okay, so here is project number 3. Now we have a light bulb and a fan. Are those two things in series or in parallel? And we know that because why?
Because you said so.
Good. Electrons flow through, every electron has to go through the fan and the light bulb. There's no pass or choices or branches, so those two things are in series. If they're in series, how does the brightness of bulb 1 compare with the brightness from the bulb in project 1? Should be dimmer, or with the speed of the fan compared to the previous part. Should be slower, because now there should be less current to increase the resistance. Since every electron has to go through two things now, electrons are going to have to move slower through the circuit, making less current means less speed and less brightness. Let's see if that's what I typed. Oops. What does, let's see if we're paying attention here, let's ask Pat. What does the sum of the potential difference across the fan and the light bulb have to add up to, do you think? Good, which was 3. Brilliant. All the potential has to get used up across the circuit. So we got the other two. We can see the current in this one is 0.6 amps. The current in the single bulb is 0.6 amps. So hopefully the current in the next project with the fan and the bulb will be less than 0.6 amps. We'll find out. Cross my fingers on this. Magic computer will do this thing now.
It's a lot of
Oh, lots.
bowling camp.
I Mrs. Feinstein.
Is that part of the recording?
No.
Steve, did you have Mrs.
Now we can see the fan is moving. Note the fan is slower here, Mark and Steve, than the fan here. And the bulb is not as bright here as it is up there. That confirms us that the current is 0.3 amps, which is less than the other two. It's only half just by coincidence.
This is superb.
All right, where's PowerPoint? Okay, so now let's talk about current in series. We just kind of did that. In series, you built this circuit for this, and you should have had a battery packing 2 light bulbs. And you're going to measure the current at different locations. How is the current related at different locations in the series circuit? All the same. Very good. In a series circuit, all charges move simultaneously. As soon as that potential difference is applied, all the charges instantly start moving through the circuit. There's no domino effect. There's no follow the leader type stuff. No leapfrogging. It all just happens at once. It's similar to a merry-go-round. Everyone here's used a merry-go-round, hopefully? Yeah. In the playground, spins in a circle. The whole thing moves at once. You can't make the person over here move faster than the person over here. As soon as we're in the merry-go-round, they're all moving simultaneously. Same thing happens in a circuit. As soon as, remember, there's always electrons inside the wires waiting to be used. Once you apply the potential difference, everything starts, moving uphill and all move simultaneously. So you can't have a faster current here, you down here, but you'll back up and log jam and a lot of good stuff.
Oh yeah, and I was showing you my water bottle.
I see that. That's what bothers me.
Want to see it?
No.
It's got a nice metal top too.
Now you could show it to me before class if you wanted to, but no.
Whoa! It could be a conductor.
The order of the elements is irrelevant to the circuit. You can put whatever order you want to put it in, but since everything's moving simultaneously, the order you put them in shouldn't affect anything, or it does not affect anything. Good. Project 4 is our first parallel project. We have a lamp and a fan that are in parallel now. The current comes, or the electrons come out the battery, get down here, and they can split into different paths. In a parallel circuit, we'll find that those two paths are independent of each other, and that each can draw as much current as it wants. Now, objects only want to generally pull so much current. So when it was all by itself, this fan was pulling 0.6 amps of current. That's as much as this fan's ever going to want to try and pull. And if the light bulb also pulls 0.6 amps of current, that's as much as it ever wants to pull. But now in parallel, they can each pull how much they want out of the battery, assuming the battery can keep up with what it's asking for. So here's a tricky question. How do you think the potential difference across the fan compares to the potential difference across the light bulb?
The same.
Why are they the same, Crystal? Okay. Good. The Randall says I'm looking for there. They all need to climb the same mountain. So every electron that's right here at point F3 eventually gets to point B3, which is the top of the mountain. So no matter what, all electrons move up 3 volts in potential. Doesn't matter if they go this way or that way. You can imagine a big mountain in front of you. You have 2 trails, one going that way, one going this way. Doesn't matter which trail you take, you're always going to get to the top of the mountain. One trail might be harder, i.e. more resistance, but it's going to be the same end result. And so one path might be faster than the other, but they're always the same potential difference. Question?
No.
Because the sun is like 100 million miles from the Earth. So let's talk about potential in parallel. The idea is that in parallel, all the potential differences are going to be the same. And so you set up this circuit over here, where you had 2 battery packs and then a light bulb in parallel with each other. Now, a lot of you still thought the potentials should have added this in the other packet. So we're going through both packets here.
Yeah, I was like that.
Oh, originally I had it like different, but it makes this explaining why this makes more sense.
Yeah.
Packet-wise, it's more confusing.
Yeah.
It's okay.
But in order to make my point about the circuit in the stat picture, I have to explain this anyways. So next year I'm going to combine these packets together somehow. It'll work better, I think. Potential in parallel. So a lot of you still thought the potential should add up across the light bulb here. But thinking about the mountain example, it doesn't really make any sense. This electron here only needs to climb 1 mountain to get to the top of the battery. If this electron all of a sudden climbed up 6 volts of mountain, it's going to end up way up here and not anywhere near the battery pack. And it's going to get lost and sad and cry, helicopters flying around, everyone will be searching for it, it'll be a big mess. If it only needs to climb as much as its battery wants to climb. So these electrons all climb up 3, these all climb up 3. Now the currents in the middle might be really big now because the current from this battery plus the current from that battery is going across the light bulb, but each individual battery will only be putting out the same amount of potential difference. Yo.
I have a question. Okay, so the electrons from the left side 3 volt battery is going up and like over, but can it go over the other way to the other battery? Is that possible? Does it have to go to the same battery?
No.
Yeah, but it's going to be negative and then the other side is positive.
No, it does not.
It does not? Like it,
So it might be the case, I don't really know what physically would happen, but I guess an electron here could go over there, but the same number will go in and out of each battery by the time you're done. Physically, I would say, I mean, assuming, I guess, we know about the world, like, we don't really know where anything is, so electron could just easily, like, once they're caught up in the middle here, they don't remember where they came from. I wouldn't think. So they can go either way. Now this setup can be better sometimes because your batteries are going to drain less quickly. You still get 3 volts of power across the light bulb, but you're going to drain up your current a little bit more slowly in parallel stuff. That's why some devices are built this way. So let's see what I typed here. Same climb, always equal, same mountain. Okay. Questions about the idea? So in 2 objects or